Have you ever looked up at the stars and wondered what truly shapes the universe? Most of what governs the cosmos remains invisible to our eyes, hidden forces weaving through space, sculpting galaxies in ways we're only beginning to understand. Right now, beneath the shimmering tapestry of the night sky, 24 unseen dynamics are at work, bending the rules of physics and rewriting the story of galactic evolution. These aren't just abstract ideas, they're the hidden architects of everything from black holes to the mysterious push of dark energy. Some of them defy logic, others challenge Einstein's theories, and all of them hold clues to the ultimate fate of our own Milky Way. Today we're pulling back the curtain on these cosmic mechanics, revealing how dark matter's ghostly grip guides entire clusters of stars, how quantum ripples can birth galaxies, and why the universe might be far stranger than we ever imagined. This isn't just astronomy, it's a detective story written across billions of light years, and you're about to uncover its most thrilling chapters. Imagine a force so powerful it holds entire galaxies together, yet it's completely invisible not just to our eyes, but to every telescope we've ever built. This is the enigma of dark matter, the universe's hidden scaffolding. Without it, galaxies would spin themselves apart, stars flung into the void like marbles rolling off a table. The first clue came from astronomer Vera Rubin in the 1970s, when she noticed something bizarre. Stars at the edges of galaxies move just as fast as those near the center, defying Newton's laws. The only explanation, an unseen mass outweighing visible matter 5-to-1, was holding everything in place with its gravitational grip. Scientists call these particles WIMP, weakly interacting massive particles, or actions, hypothetical specks that pass through ordinary matter like ghosts through walls. But here's where it gets eerie. Supercomputer simulations like those from the Illustris project reveal dark matter isn't just floating aimlessly, it forms a vast cosmic web, filaments of shadow stretching across the universe, guiding galaxies into place like beads on an invisible string. Yet after decades of searching, we still don't know what dark matter truly is. Could it be whispering to us through unknown forces, or hiding dimensions we can't yet perceive? The answer might rewrite not just galactic evolution, but the very laws of physics. But while dark matter keeps galaxies anchored, something far stranger is happening on an even grander scale. An unseen force not pulling the universe together, but tearing it apart. In the late 1990s, two teams of astronomers made a discovery so shocking, it upended everything we thought we knew about cosmic fate. By studying distant supernova exploding stars that act as cosmic mile markers, they found the unthinkable. The universe wasn't just expanding, it was accelerating. The culprit, dark energy, a mysterious repulsive force making up roughly 68% of the cosmos, overwhelming gravity's pull. Imagine blowing up a balloon with invisible ink as it inflates. Galaxies scrawl farther apart, their speed increasing as if pushed by an unseen hand. This revelation earned scientists the Nobel Prize, but the mystery only deepened. Einstein once proposed a cosmological constant, a static energy woven into space itself. Yet some theorists argue dark energy might be quintessence, a dynamic field that fluctuates over time. The stakes couldn't be higher. If dark energy strengthens, it could shred galaxies in a big rip, unraveling atoms themselves. If it weakens, gravity might reverse expansion, collapsing the cosmos into a big crunch. But here's the real twist. Recent Hubble telescope data suggests dark energy's strength might vary across space-time, hinting at undiscovered dimensions or even flaws in Einstein's relativity. One thing's certain, the fate of the universe depends on an invisible force we're only beginning to measure. Now picture a universe so turbulent that even empty space isn't really empty, where particles flicker into existence for mere fractions of a second, before vanishing like cosmic fireflies. This is the quantum foam, the seething foundation of reality itself, and it holds the third great mystery shaping galactic evolution. In the earliest moments after the Big Bang, these fleeting quantum fluctuations, tiny ripples in spacetime, left permanent fingerprints on the cosmos. Imagine blowing on the surface of a still pond. Those faint disturbances eventually grow into waves. Similarly, microscopic density variations, imprinted by quantum uncertainty, became the seeds for all structure in the universe. When scientists mapped the cosmic microwave background, the afterglow of the Big Bang, they found those exact patterns, temperature variations matching predictions from quantum theory down to 1 part in 100,000. It was Nobel Prize-winning proof that galaxies, clusters, and even the vast cosmic web owe their existence to these ghostly subatomic tremors. Stephen Hawking revolutionized our understanding by revealing how quantum effects near black holes, now known as Hawking radiation, could arise from similar vacuum fluctuations. Laboratories today recreate these conditions using Casimir plates, where mirrors placed closer than a hair's width apart suppress certain quantum vibrations, proving empty space exerts real, measurable pressure. But the most mind-bending possibility, these same quantum ripples might not just shape our universe, they could spawn entirely new ones. Some theories suggest every fluctuation creates branching timelines, a multiverse where infinite cosmic stories unfold simultaneously. Whether spawning galaxies or alternate realities, one truth emerges: the smallest quantum whisper can echo across eternity. Hidden beneath the glow of stars and nebulae, another invisible architect is at work. Threads of magnetism, so vast they stitch galaxies together. These aren't the simple bar magnets of a high school experiment. They're colossal force fields stretching tens of thousands of light years, twisting through interstellar space like cosmic spider silk. NASA Fermi telescope caught their ghostly fingerprints by detecting synchrotron radiation, high-energy light emitted when electrons spiral along magnetic field lines at nearly the speed of light. This revealed a stunning truth: magnetic webs don't just fill galaxies, they connect them, guiding rivers of gas into stellar nurseries where new suns ignite. Picture a cosmic puppet master pulling strings. Without these fields, gas would collapse chaotically, and star formation might grind to a halt, but the real mystery lies in their origin. Some galaxies, like our Milky Way, boast elegant spiral magnetic patterns, as if woven by some celestial loom. Others, like the chaotic starburst galaxy M82, have fields so turbulent they resemble a stormy sea. Could these forces trace back to the Big Bang itself, frozen into the fabric of space during the universe's fiery birth? Or are they forged later, sculpted by the violent jets of supermassive black holes? Recent simulations show both might be true primordial seeds amplified by galactic dynamos, turning entire galaxies into self-sustaining electromagnetic engines. Either way, one thing's clear: magnetism isn't just a footnote in cosmic history, it's a hidden conductor, orchestrating the birth of stars and the fate of galaxies in silence. Every second, trillions of ghostly particles pass through your body without a single trace. Neutrinos, the universe's most elusive travelers, born in the hearts of stars and the wreckage of cosmic collisions. Though they carry no charge and barely interact with matter, these subatomic wraiths might hold the key to one of galactic evolution's quietest mysteries. In 2013, the IceCube Observatory buried deep in Antarctic ice made a staggering discovery: high-energy neutrinos, billions of times more powerful than our suns, streaming from blazars like TXS 0506 plus 056, active galaxies with supermassive black holes firing particle jets directly at Earth. These detections revealed something profound: neutrinos aren't just passive spectators, they ride shockwaves from dying stars, threading through galaxy clusters, subtly influencing how matter clumps together over eons. Picture a cosmic river, silent, invisible, yet strong enough to nudge the distribution of galaxies by fractions that compound over billions of years. but the plot thickens. Some neutrinos might not even play by known physics rules. Hypothetical, sterile neutrinos, if they exist, could interact only through gravity, making them prime dark matter suspects. Experiments like the upcoming Deep Underground Neutrino experiment aim to catch these phantoms in action. If successful, we might solve two cosmic riddles at once: why galaxies cluster the way they do, and what dark matter truly is. But neutrinos are just one piece of the particle puzzle. What if the universe's very first black holes weren't born from dying stars, but from the explosive chaos of the Big Bang itself? These hypothetical primordial black holes, some no heavier than an asteroid yet dense enough to crush mountains into pinheads, could be lurking everywhere, invisible architects shaping galaxies from the shadows. Unlike their stellar-born cousins, these ancient relics might have formed in the first chaotic seconds of time, when extreme pressures could collapse matter directly into black holes without needing stars at all. When LIGO detected gravitational waves from merging black holes in 2015, scientists were stunned by their masses, some clocking in at tens of solar masses, far heavier than expected. Could these be echoes of primordial monsters, survivors from the dawn of time? Some theorists take it further, suggesting these hidden black holes might solve two cosmic mysteries at once. If enough of them exist, their combined gravity could account for dark matter's invisible pull. Even wilder, a Neptune-sized primordial black hole might explain the strange orbits of objects beyond Pluto, an alternative to the hypothetical planet 9. The James Webb Space Telescope could soon hunt for their telltale signatures, flickering stars briefly magnified by unseen black holes passing in front of them. Whether galaxy seeds, dark matter, or cosmic wanderers, these time capsules from the Big Bang remind us sometimes the universe hides its greatest architects in the smallest, darkest corners. There's a rhythm to the cosmos, an ancient echo frozen in time, stretching 500 million light-years across the sky. These are Baryon acoustic oscillations, the universe's fossilized sound waves, and they're giving us a yardstick to measure the very fabric of space. Picture the early universe as a seething plasma soup, photons and particles locked in a violent tug of war. When the first sound waves rippled through this primordial fluid, they left indelible fingerprints, regions where matter clumped together in spherical shells, like ripples around a pebble dropped in a pond. Fast forward 13.8 billion years, and those ripples are still visible. The Sloan Digital Sky Survey's galaxy maps reveal something astonishing. Galaxies today are slightly more likely to be found at a precise distance from one another, about 500 million light-years apart, a relic of those primordial sound waves. It's as if the universe whispered a secret in its youth, and we're just now learning to listen. But these oscillations aren't just cosmic archaeology, they're a precision tool. By measuring how this standard ruler appears stretched or squeezed at different eras, astronomers can track how dark energy has warped the universe's expansion. The results chillingly precise. Like a cosmic speedometer, Baryon acoustic oscillations confirm dark energy's acceleration with razor-sharp certainty, matching supernova data while offering an independent check. Some theories even suggest these patterns could reveal if dark energy changes strength over time, a clue to whether the universe will end in ice or fire. From sound waves to galaxy clusters, the universe's hidden melodies are still guiding us toward truths we've only begun to hear. Think of the universe's first moments not as a slow unfurling, but as a sudden, breathtaking explosion of space itself, a growth spurt so violent it stretched a subatomic speck into a cosmos in less time than it takes light to cross a single proton. This was cosmic inflation, a theoretical heartbeat of exponential expansion that may have set the stage for everything we see today. In that fleeting instant, just 1/1,000,000,000 of a trillionth of a trillionth of a second after the Big Bang, space ballooned by a factor of 10 to the power of 26, stretching quantum ripples into vast density variations that later became galaxies. Picture blowing up a balloon covered in microscopic ink dots. As it inflates, those tiny marks stretch into continent-sized patterns. That's precisely how subatomic quantum jitters, magnified by inflation's relentless pull, became the cosmic scaffolding for galaxy clusters. The echoes of this event might still be visible in the cosmic microwave background, where telescopes like BICEP hunt for faint swirls in polarized light, called B-modes. That could be the gravitational wave fingerprints of inflation itself. But here's where the plot twists. When BICEP 2 announced a detection in 2014, it sparked euphoria until interstellar dust muddied the signal. Yet even the controversy reveals something profound. Inflation's energy scales point to energies so extreme they hint at unified physics beyond the standard model, perhaps even string theory vibrations from higher dimensions. And if inflation truly happened once, could it happen endlessly? Some models suggest our universe is just one bubble in a frothing multiverse sea, where new cosmic domains sprout eternally, each with different physical laws. Whether inflation left its mark on the sky or hides in deeper data, one thing's certain: the universe's first unimaginable growth spurt didn't just shape galaxies. It might have written the rulebook for reality itself. Time doesn't tick the same way everywhere in the universe. Near a massive galaxy, it literally slows down, warped by gravity's invisible hand. This isn't science fiction, it's Einstein's general relativity in action, where the fabric of spacetime itself bends under the weight of matter, stretching seconds into what feels like hours for distant observers. The Hubble Space Telescope has captured jaw-dropping proof: eerie Einstein rings, perfect circles of light formed when a foreground galaxy's gravity bends light from objects behind it like a cosmic magnifying glass. These rings aren't just stunning visuals, they're cosmic clocks, revealing how time drags near massive objects. One study clocked time running 5 times slower near a supermassive black hole compared to Earth. But here's the real puzzle: dark matter's gravitational grip is even stronger than visible matter's. If we could place a clock deep inside a galaxy's dark matter halo, would it tick at half speed? A 10th simulation suggests these halos might warp time so dramatically that signals from their cores could reach us stretched into deep, distorted echoes. Even stranger, this time warp isn't just a curiosity, it could explain why some galaxies appear frozen, in early states of evolution, when we observe them. Their light left eons ago, but their clocks were running slower all along, warping our perception of cosmic history. From bending light to stretching time, relativity's hidden fingerprints are everywhere, quietly rewriting the rules of how we see the universe's story unfold. Deep in the cosmic shadows, galaxies engage in a silent feast, swallowing their neighbors whole in acts of gravitational cannibalism that shape the universe's largest structures. Our own Milky Way is no innocent bystander. It's a seasoned predator with the stellar equivalent of bones still scattered across its halo. The European Space Agency's Gaia spacecraft has mapped these celestial crime scenes in stunning detail, revealing ghostly streams of stars, twisted ribbons winding through our galaxy like cosmic DNA. These are the remnants of dwarf galaxies torn apart over billions of years, their stars still tracing the exact paths of their final orbits like fingerprints on a galactic murder weapon. One famous victim, the Sagittarius dwarf spheroidal, has been stretched into 4 distinct streams wrapping around the Milky Way, its stars moving in perfect unison despite being separated by thousands of light years. Computer simulations show this isn't gentle assimilation, it's violent disintegration. As smaller galaxies approach, tidal forces stretch them into spaghetti-like filaments, a process astronomers poetically call tidal disruption. The Gaia team recently identified the remnants of at least 6 such meals in our galaxy's history, including one colossal collision just 8 to 10 billion years ago that may have given the Milky Way its thick stellar disk. But this feast isn't unique to our corner of space. Look at the giant elliptical galaxy Messier 87, and you'll see it's not just eating small galaxies, it's consuming entire clusters, growing fat on mergers like a cosmic cronut absorbing its neighbors. These collisions don't just reshape galaxies, they trigger starbursts, reignite dormant black holes, and scatter heavy elements across intergalactic space. The terrifying beauty, our galaxy's hunger ensures its own eventual demise. In about 4 billion years, the Milky Way will become the prey as Andromeda's far greater mass tears us apart in the ultimate cosmic showdown, a merger that will rewrite the night sky forever. At the heart of nearly every galaxy, a sleeping giant lurks, supermassive black holes with appetites so vast they can alter the destiny of entire star systems. But when these cosmic monsters awaken, they don't just consume, they sculpt. Chandra X-ray Observatory's razor-sharp vision has revealed something astonishing. High-energy jets blasting from active black holes act like cosmic blowtorches, heating surrounding gas to millions of degrees until it's too turbulent to collapse into new stars. Astronomers call this feedback, a delicate balancing act where the black hole's fury becomes the galaxy's thermostat. Picture a superheated bubble inflating in the heart of a galaxy, its shockwaves pushing star-forming gas outward like a cosmic plow, leaving behind a red and dead, elliptical galaxy where star formation has been quenched. The evidence is etched across the universe. Compare the Sombrero Galaxy with its dormant central black hole to the chaotic quasar 3C273, one a quiet elder, the other a fire-breathing youth. In the latter, X-ray images show vast cavities carved by jets spanning hundreds of thousands of light years, while infrared data reveals star formation rates plummeting as the black hole's fury sterilizes its surroundings. But here's the twist, this destruction breeds creation. Those same jets can trigger shockwaves that compress gas in distant regions, sparking new stellar nurseries at the galaxy's edges like cosmic dominoes. It's a dance of chaos and order, where the universe's most destructive force also holds the blueprints for rebirth. Some theories even suggest black hole feedback solves a long-standing mystery, why the largest galaxies aren't even larger, their growth stunted by their own heart's violent outbursts. From star-forming factories to cosmic graveyards, these invisible gravitational maestros prove destruction and creation are two sides of the same coin. Some cosmic mysteries don't just hide in darkness, they wear its disguise, masquerading as black holes while playing by entirely different rules. Meet exotic compact objects, the universe's most convincing impersonators. When LIGO detected gravitational waves from collisions in the so-called mass gap, objects too heavy for neutron stars yet too light for typical black holes, it sparked a hunt for theoretical oddities that could rewrite the stellar rulebook. At the top of the list are quark stars, stellar remnants so dense they crush protons and neutrons into a seething soup of free quarks, the universe's most fundamental building blocks. Imagine a sugar cube weighing as much as Mount Everest, its matter compressed beyond atomic structure into a bizarre quantum state called strange matter. Some theories suggest these stars could form when neutron stars absorb dark matter or collide, triggering a phase transition that turns them into ultra-dense quark globes. But there's an even stranger candidate: gravastars, hypothetical objects with a shell of ultra-condensed matter surrounding nothing. Picture a soap bubble where the surface tension is gravity itself, trapping a vacuum inside that defies Einstein's equations. Unlike black holes, these would have no singularity or event horizon, instead bending spacetime so sharply light barely escapes. The smoking gun, gravastars might produce gravitational wave echoes after collisions, tiny ripples LIGO could detect in future upgrades. Even more intriguing are boson stars, theoretical orbs made entirely of dark matter particles, glowing faintly from their own quantum vibrations. While black holes cast shadows in telescope images, exotic compact objects might reveal themselves through subtle differences, warmer surfaces, unusual X-ray flickers, or gravitational lensing quirks. The next time LIGO catches a mass gap signal, it might not be a black hole at all, but something far stranger, a cosmic shapeshifter rewriting our understanding of how matter behaves under extreme gravity's grip. What if dark matter doesn't exist at all, and the real mystery is gravity itself? A rebellious faction of physicists argues we've been chasing ghosts when the answer was hidden in plain sight. Gravity might simply work differently on cosmic scales. This radical idea, called modified Newtonian dynamics, Orman suggests Einstein's equations need a tweak when dealing with the faint tugs between stars and galaxies. Picture a car that inexplicably speeds up when you take your foot off the gas. That's how stars behave at galaxy edges, orbiting faster than Newton's laws predict. While most scientists blame unseen dark matter for this cosmic speed limit violation, when proponents rewrite the rulebook entirely, their equations introduce a tiny adjustment, a gravitational boost that kicks in when accelerations dip below 1/10,000,000th of Earth's gravity, a threshold so low it only affects galaxy outskirts. Early wins seemed promising. Men nailed the rotation curves of dozens of spiral galaxies with uncanny precision, no dark matter required, but then came the bullet cluster, a cosmic collision that became the ultimate courtroom for this gravitational debate. When Chandra X-ray Observatory mapped this wreckage of two galaxy clusters, it revealed something startling. Most of the mass, traced by gravitational lensing, had sailed right through the collision like phantom boxers, while hot gas, the visible matter, piled up in the center. To dark matter believers, this was proof positive. Invisible mass had separated from regular matter. Men supporters fired back, tweaking their models to include neutrino-like particles, but the elegance of their original vision frayed. Subsequent galaxy observations deepened the rift. Some ultra-diffuse galaxies defied men predictions entirely, spinning far slower than the theory allowed. Yet in 2020, a bombshell: researchers found galaxies where stars move as if men rules apply even when they shouldn't, a phenomenon dubbed men-like behavior in Newtonian systems. The plot thickens with quantum gravity theories like Verlin's emergent gravity, suggesting gravity isn't fundamental but arises from entangled quantum bits, a framework that oddly mirrors men predictions. Whether gravity's laws need revision or dark matter's shadowy grip is real, one truth emerges: the universe loves to humble us, revealing that even our most trusted equations might be placeholders for deeper, stranger truths. Buried in the fabric of space-time itself, there might be cracks, remnants of the universe's fiery birth so strange they could slice through reality like cosmic razor wires. These are cosmic strings, hypothetical one-dimensional defects in spacetime, thinner than a proton yet stretching across the entire observable universe, each carrying the mass energy of millions of suns. Picture the early cosmos cooling from its initial chaos, like ice forming on a pond, except as spacetime froze, it might have trapped fractures in its structure, flaws where the rules of physics twist ever so slightly. If they exist, these strings would warp spacetime around them, creating bizarre gravitational lenses that distort background galaxies into double images. The European Space Agency's Planck satellite may have already spotted their fingerprints in the cosmic microwave background, anomalous temperature patterns that align in ways ordinary inflation can't explain. But the most mind-bending possibility: cosmic strings could have been galactic puppet masters. Simulations show these ultra-dense filaments would have acted as gravitational scaffolding in the early universe, funneling gas into dense ribbons where galaxies formed in eerie, string-like arrangements. Some astronomers even suggest the vast Hercules Corona Borealis Great Wall, a colossal filament of galaxies over 10 billion light-years long, might trace the path of an ancient cosmic string. And here's where it gets stranger. Unlike black holes or dark matter, these defects could vibrate, sending out gravitational waves detectable by observatories like LISA. Some theories propose strings might even snap, releasing bursts of energy so powerful they briefly outshine entire galaxies. Whether fossilized relics or active players, cosmic strings remind us that the universe's grand design might be written in flaws we're only beginning to trace. Deep in the swirling chaos around black holes, where gravity bends light into impossible loops, a ghostly particle might be revealing itself, not through direct detection, but through its absence. These are action-like particles, hypothetical dark matter candidates so elusive they could slip through Earth by the billions every second without leaving a trace. Unlike traditional particles, actions are theorized to be virtually massless, interacting so weakly with normal matter that they're almost more like ripples in spacetime than solid objects. But near supermassive black holes, their invisibility might finally crack. The Event Horizon Telescope, famous for capturing the first image of a black hole silhouette, noticed something odd in the polarized light swirling around M87's core, anomalous twists that conventional physics can't fully explain. One tantalizing possibility: actions transforming in the black hole's extreme magnetic fields, morphing into photons and leaving faint but detectable imprints in the polarized glow. Think of it like ice melting into water, except here, an invisible particle flickers into visible light under gravitational pressures so intense they warp the rules of quantum mechanics. These signals could solve two cosmic puzzles at once: the nature of dark matter and the bizarre behavior of light near event horizons. Laboratories like ADNX are hunting for actions on Earth by tuning superconducting cavities to listen for their faint electromagnetic whispers. But black holes might be nature's ultimate particle accelerators, magnifying effects too subtle to measure anywhere else. If confirmed, actions wouldn't just be another particle, they'd be a cosmic shapeshifter, bridging the gap between quantum physics and the hidden architecture of the universe. And the strangest part, their existence might trace back to a symmetry-breaking moment in the early universe, a flaw in spacetime's fabric so perfect it's been hiding in plain sight for 13.8 billion years. What if every galaxy, star, and planet we see is nothing more than an illusion, a cosmic mirage projected from a hidden two-dimensional surface? This is the holographic principle, one of physics' most radical ideas, suggesting our three-dimensional universe might be encoded on a distant boundary like a movie projected from a flat screen. The first clues came from black holes of all places, where physicist Jacob Bekenstein discovered something astounding: a black hole's entropy, its measure of disorder, doesn't scale with its volume but with its surface area. Imagine writing all the information about objects swallowed by a black hole not within its depths, but on its event horizon, like data etched onto a celestial hard drive. Nobel laureate Gerard T. Hooft and Leonard Susskind took this further, proposing that the entire universe might operate the same way, with every particle, every force, every spark of consciousness potentially reducible to flickering bits on some unimaginably vast two-dimensional surface at the edge of spacetime. Think of it like a credit card hologram, flat at first glance, but tilting it reveals dizzying depth. String theory calculations support this, showing how higher dimensional physics can emerge from lower dimensional frameworks, much like how a 3D video game renders immersive worlds from flat code. But here's where it gets eerie. If the holographic principle holds, it could mean reality as we experience it is a kind of cosmic projection, a shared hallucination woven from information too fundamental for our senses to grasp directly. Some scientists speculate this might even lend credence to simulation theories, the idea that our universe could be an advanced computational construct, with galaxies as pixels in an alien supercomputer. Yet whether literal or metaphorical, the holographic principle forces us to confront a staggering possibility: the deepest truths of existence might not lie in the stars above, but in the invisible data written on the walls of reality itself. On August 17, 2017, the universe gave us front-row seats to a cosmic alchemy show, one where two dead stars collided in a blaze of gold and platinum, rewriting the periodic table in real time. LIGO gravitational wave detectors caught the first ripple, a telltale chirp lasting 100 seconds as two neutron stars spiraled toward each other at 1/3 the speed of light. But this wasn't just another collision. Within seconds, telescopes across Earth and space swung into action, capturing the aftermath in gamma rays, X-rays, even visible light, a first in multi-messenger astronomy. The data revealed something astonishing: a kilonova, a fireball 1,000 times brighter than a typical nova, glowing blue then red as it spewed out material at relativistic speeds. Spectroscopy confirmed the presence of strontium, gold, and platinum-heavy elements forged in the neutron-rich debris. Picture two city-sized stars, each so dense a sugar cube's worth weighs more than Mount Everest, smashing together with enough force to briefly outshine all the stars in the observable universe combined. The shockwaves from such events rip apart atomic nuclei, creating a neutron soup where rapid neutron capture, the AR process, builds elements heavier than iron in seconds. Simulations show a single merger can produce up to 100 Earth masses of gold alone, scattering it across interstellar space like cosmic glitter. But GW170817 was just the beginning. By analyzing the event's gravitational wave signature, astronomers pinned down the neutron star's combined mass to within 1%, proving these collisions are factories for the universe's heaviest elements. Even more intriguing, the leftover debris likely collapsed into a black hole, suggesting a hidden link between the birth of these cosmic vacuums and the seeding of galaxies with precious metals. From wedding rings to nuclear reactors, the remnants of ancient neutron star mergers are all around us, silent witnesses to a universe that builds beauty from destruction. There's a storm raging across the cosmos, one so fierce it can strip galaxies of their star-forming fuel in a cosmic heartbeat. These aren't the gentle breezes of a summer day, but galactic winds, hurricanes of superheated gas blasted outward by supernova and black holes at speeds topping millions of miles per hour. The Atacama Large Millimeter Array recently captured one of these tempests in shocking detail, a molecular outflow from galaxy Messier 82, where newborn stars are simultaneously birthing and starving their own future. Picture a wildfire that burns down its own forest. Each exploding supernova propels vast clouds of gas into intergalactic space, a self-destructive cycle where star formation sows the seeds of its own famine. The numbers are staggering. In starburst galaxies like these, winds can eject the mass equivalent of 10 suns every year, draining reservoirs that would have fueled thousands of future stars. Ulmer radio eyes revealed the invisible chemistry of this exodus: carbon monoxide molecules fleeing at 700 kilometers per second, a telltale sign of gas too turbulent to collapse into new stellar nurseries. But here's the twist: these winds don't just destroy, they connect. When NASA Chandra X-ray Observatory mapped the Perseus cluster, it found vast tendrils of enriched gas spanning hundreds of thousands of light years, the cosmic equivalent of a garden sprinkler, dispersing heavy elements forged in supernova across intergalactic space. This recycling might explain a long-standing mystery: why galactic halos contain enough hot gas to build multiple generations of stars, yet remain stubbornly diffused. Some theories suggest these winds create galactic fountains, where ejected gas eventually cools and rains back down, sparking new star formation eons later. From annihilation to rebirth, these invisible tempests prove even the universe's most destructive forces are part of a grander, self-regulating dance. Somewhere in the universe right now, a star is experiencing the ultimate cosmic torture, stretched into a luminous ribbon of plasma as a black hole's gravity peels it apart layer by layer. These are tidal disruption events, nature's most violent light shows, where a single star's death throes can briefly outshine every star in its host galaxy combined. In 2019, astronomers witnessed one such cataclysm in unprecedented detail, a supermassive black hole 200 million times the mass of our Sun, snacking on a star in the galaxy 2 billion light-years away. The Zwicky Transient Facility, a robotic sky survey in California, caught the first flicker of this stellar carnage, designated at 2019 KIS. What followed was a masterclass in cosmic destruction. As the star ventured too close, tidal forces, the same phenomenon that creates Earth's ocean tides but amplified by a factor of billions, stretched it vertically while compressing it horizontally, a process astronomers grimly call spaghettification. The star's outer layers were torn free, swirling into a glowing accretion disk hotter than the surface of our Sun, while its surviving core whipped around the black hole at relativistic speeds like a cosmic slingshot. For weeks, this stellar debris blazed across the electromagnetic spectrum, from X-rays to radio waves, offering scientists a ringside seat to physics at its most extreme. But the real surprise came when researchers analyzed the event's polarization, the alignment of its light waves. Unlike typical supernova, at 2019 KIS's light was startlingly polarized, revealing a donut-shaped structure of ejected material billowing outward at 10% the speed of light. These observations confirmed a long-held theory: tidal disruption events don't just feed black holes, they sculpt their surroundings, launching jets of matter that can influence star formation across entire galactic neighborhoods. With next-generation observatories like the Vera Rubin Observatory coming online, astronomers expect to catch hundreds more of these cosmic feeding frenzies, each one a laboratory for testing relativity, plasma physics, and the very limits of how matter behaves under gravity's most unforgiving grip. What if dark matter isn't just invisible but also warm? Unlike the sluggish, cold dark matter particles that dominate most theories, warm dark matter would zip through space at nearly 1% the speed of light, altering how galaxies are born in ways we're only starting to understand. Picture two artists sculpting the same clay, one working with thick, slow-moving wax, the other with fast-drying plaster. That's the difference between cold and warm dark matter in shaping the cosmos. Supercomputer simulations reveal this speed changes everything. Cold dark matter, heavy and slow, clumps easily into dense halos that act as gravitational anchors for galaxies. But warm dark matter, lighter and faster, would smooth out those clumps, creating a cosmic landscape where dwarf galaxies are rarer and more evenly spaced, like skipping stones across a pond instead of dropping them in one spot. The evidence might lie in the Lyman alpha forest, a bizarre pattern in quasar light where absorption lines from hydrogen clouds create a forest of spectral lines. These clouds trace the cosmic web's filaments, and their distribution hints at whether dark matter's warmth suppressed small-scale structures early on. Some observations, like the unexpected scarcity of dwarf galaxies around the Milky Way, align eerily well with warm dark matter predictions. Others, like the intricate patterns in the cosmic microwave background, still favor colder versions. The debate isn't just academic. If dark matter is warm, it could mean these elusive particles are lighter than a neutrino, perhaps even interacting through forces we've yet to discover. From dwarf galaxies to quasar light, the universe might be whispering that dark matter's story is far richer and faster than we ever imagined. Bursting from the hearts of active galaxies, torrents of high-energy particles streak across the cosmos at nearly the speed of light and cosmic rays, the universe's silent regulators. These aren't just random high-speed projectiles, they're a feedback mechanism so potent it can stifle star formation across entire galaxies. When a supermassive black hole in an active galactic nucleus erupts, it doesn't just spew light, it launches protons and atomic nuclei with energies dwarfing anything our most powerful particle accelerators can produce. The Pierre Auger Observatory in Argentina, a sprawling array of detectors covering 3,000 square kilometers, has captured these extraterrestrial bullets with energies exceeding 100 exie-electronvolts. That's a macroscopic grain of sand packed with the kinetic energy of a fast-pitched baseball. But here's where it gets fascinating. As these particles rain down on a galaxy's gas clouds, they don't just pass through. They ionize the gas, heating it turbulently and preventing it from cooling into the dense pockets needed for new stars. Picture blowing on a bowl of hot soup to cool it, except instead of steam, you're showering it with particle shrapnel that keeps it perpetually stirred up. Observations of galaxies like Centaurus reveal vast lobes of radio emission, the afterglow of cosmic ray-driven winds stretching millions of light-years, effectively pressing a pause button on stellar birth. Simulations show this feedback is exquisitely balanced. Too weak and galaxies would overproduce stars, too strong and they'd become sterile wastelands. Some theories even suggest cosmic rays could solve the missing satellite problem. Their relentless pressure might explain why small galaxies around the Milky Way are far fewer than cold dark matter models predict. From particle physics to galactic ecology, these invisible bullets prove the cosmos isn't just shaped by gravity's pull, but by the relentless push of high-energy particles rewriting the rules of stellar life and death. Between the galaxies, where the void seems empty and still, an invisible ocean churns, a seething soup of magnetized plasma sculpting the cosmos in ways we've only begun to map. This isn't just scattered gas, it's a superheated ionized labyrinth where charged particles spiral along magnetic field lines at nearly light speed, creating instabilities so powerful they can rewrite the fate of entire galaxy clusters. The Chandra X-ray Observatory peeled back the curtain on this chaos when it detected giant sound waves rippling through the Perseus cluster, not true sound, but pressure waves propagating through plasma, each spanning tens of thousands of light years. Picture dropping a boulder into a lake, except the ripples are so vast they could swallow our solar system whole. These waves are cosmic fingerprints, revealing how black hole jets inject energy into surrounding plasma, stirring it into turbulent whirlpools that regulate how clusters grow. But the real breakthrough came when simulations matched these observations, showing how plasma instabilities like the magneto-rotational effect act as cosmic mixers, redistributing heat so efficiently that some galaxy clusters stay hotter than expected for billions of years. The upcoming Athena mission, set to launch in the 2030s, will take this investigation further. Its X-ray eyes resolving plasma motions with unprecedented clarity, potentially catching magnetic reconnection events in action. These are the moments when field lines snap and reconnect, unleashing energy akin to millions of supernovae in seconds. Scientists suspect these instabilities might explain why some clusters glow strangely bright in X-rays, while others appear mysteriously dim. From regulating star formation to channeling black hole energy across cosmic distances, plasma's hidden turbulence proves that even the emptiest corners of space are alive with unseen forces, rewriting the rules of galactic evolution one magnetic whirlpool at a time. Gravity might not be a fundamental force at all. Instead, it could be the universe's ultimate illusion, a side effect of something far stranger playing out in the quantum shadows. This radical idea, known as entropic gravity, flips everything we thought we knew about cosmic attraction on its head. Picture a stretched rubber sheet representing space-time, with massive objects creating dents that pull things inward. Now erase that sheet entirely. What if gravity isn't coming from warped geometry, but from the way information itself rearranges at the smallest scales? That's the bold claim made by physicist Eric Verland, who argues gravity emerges from the natural tendency of quantum systems to maximize entropy, their disorder. Think of it like a cosmic game of Tetris. As particles interact, they constantly seek the most probable, disordered arrangements, and this statistical push creates what we perceive as gravitational pull. Verlin's equations suggest dark matter's effects could just be this entropic tug in disguise, eliminating the need for invisible particles altogether. When applied to galaxy rotation curves, his model eerily matches observations without invoking dark matter, as if the universe's hidden structure is written in quantum probabilities rather than unseen mass. Critics point to gaps like explaining the bullet cluster's gravitational lensing, but supporters counter that entropic gravity might unify quantum mechanics and relativity in ways we're only beginning to grasp. After all, black holes already taught us that gravity, entropy, and information are deeply entangled. If Verlin's right, the force that shapes galaxies could be nothing more than the universe's relentless drive toward chaos, a cosmic housekeeping effect written into the fabric of reality itself. Phantom energy isn't just another cosmic mystery, it's a hypothetical doomsday scenario hiding in plain sight, a force so relentless it could unravel the very fabric of reality. Unlike the dark energy we know, which pushes galaxies apart at an ever-increasing pace, phantom energy would ramp up its destructive power over time, growing stronger as the universe expands. Picture a rubber band stretched too far, except instead of snapping back, it keeps stretching until even the atoms holding you together are torn apart in a cataclysm cosmologists call the Big Rip. The mathematics behind this nightmare are chilling. If dark energy's repulsive force has an equation of state where its pressure-to-density ratio drops below -1, it would trigger an exponential feedback loop. Space wouldn't just expand, it would accelerate its own expansion infinitely, shredding galaxy clusters first, then galaxies, stars, planets, and finally, nuclei within atoms themselves, all in the span of about 22 billion years. Recent data from the Dark Energy Spectroscopic Instrument, or DESI, is putting these apocalyptic models to the test. By mapping 37 million galaxies and quasars across 11 billion years of cosmic history, DESI has narrowed dark energy's equation of state to -0.99 plus, or -0.04, hovering dangerously close to the phantom threshold without definitively crossing it. Yet some intriguing anomalies linger. Certain supernova measurements hint at fluctuations in dark energy's strength over time, as if the universe's ultimate fate hasn't been fully decided. If phantom energy is real, its fingerprints might hide in the subtle warping of spacetime around ancient galaxy clusters, or in the way distant supernova appear dimmer than expected. The implications are staggering. A big rip wouldn't just end life, it would erase the physical laws making life possible, leaving behind a cold, empty void where even the concept of time loses meaning. Whether DESI next data release brings clarity or deeper mystery, one truth remains: the universe's darkest energy might not just shape our future, it could erase it entirely.